Hello guys, we will be discussing briefly about Ohm's law and few related questions. Okay, depending on your doubts, we will be discussing few questions based on current instant drift velocity as well. Okay, yes. Is it clear? In this session, we will be discussing the basic concepts of current electricity, that is current density, drift velocity, Ohm's law, related points like dependency.
Just in a minute, we can even recollect back that also. Electric current. Electric current is defined as the rate of flow of charge through a given cross section. Normally, you can write it as dq by dt. And this current can also consider as average current and instantaneous current. If you say average current, you can say simply total charge by total current. So total charge by total time. As instantaneous current, if you say, then we can say, you can also write it as total charge, you can write it as delta Q by delta T also. Mathematically, you can express it this way. As instantaneous current can be expressed as limit delta Q by delta T as delta T tends to 0 will be taken as instantaneous current. This can be given as dq by dt also mathematically. Delta T tends to 0 means when the time interval becomes very small. So the same concept we have used in the motion in straight line while discussing instantaneous velocity. Right. And this current you can calculate in different cases, like when a charged particle is moving in a circular path. You can say a time taken by the charged particle to complete one rotation is called time period. If it is having radius r, if it is moving with velocity v in this path, the charged particle having charge q, then time period is given as what? Distance by speed. Distance is 2 pi r, by speed is v. So from this, by making use of this, you can calculate the current produced by this. The equivalent current I is equal to q by time period. This can also be taken as time period. If you substitute here, you write 2 pi r by v, and you can write qv by 2 pi r. You can use to calculate the time. In terms of frequency also, you can write this as 1 by t, you can take as frequency, and once 2f you can write. And in terms of angular frequency also, you can mention this. Angular frequency is omega equal to 2 pi f. Omega is equal to 2 pi f. F is equal to omega by 2 pi. Hence, we can write q omega by 2 pi. Q is f is equal to omega by 2 pi. So f is omega by 2 pi. 2 omega by 2 pi also can take to calculate the current. So these are different ways of calculating currents, right? Whereas current density is current per unit area at a point in a conductor gives current density. Current density. It is denoted by the symbol J, and it is a vector quantity. The board is not visible online. So let us look here only. Current density is defined as, current density J is defined as current per unit area. Current per unit area. So a small cross section, if you are dealing with small cross section dA, then write a small current dI by dA will take. And it is a vector quantity, it will be along the direction of inside the current or area vector which we are considering. Right? So from this you can also write a dI is equal to J dA, or in vector form J vector dot dA vector. Dot product of these two will give you current. If you want the total current to the conductor and integrate, then you will get integral of dI is I is equal to integral of J vector dot dA vector also can write. This further you can also write it as J dA cos theta. If area vector of a given point is making an angle theta with the direction of flow of current, or with the direction of normal of that particular cross section, then you can express either way this way or this way. Well, depending on the question data in the question, you can use whether this or this to calculate current by using current density. So if you observe this, and if you compare with the flux, what do you call the concept of flux? Flux is equal to EA cos theta electric flux, BA cos theta magnetic flux. So electric flux gives in terms of electric field, magnetic flux will be expressed in terms of magnetic field. And in terms of current density you are expressing. Current density into area into cos theta. So this can be current can be taken as current density flux, or flux of current density can also be taken as current. Right? This is briefly about some what do you call it? Interrelation between current and current density and how to calculate it. Now let us see what is this drift velocity. Drift velocity. If you have a conductor, current carrying conductor, usually at room temperature, due to thermal energy, all conductors will be in random motion and hence current will be zero. If you connect this to an external source called battery of potential difference V, it establishes some field E. So because of this field, electrons will be drifted from one end to another end in opposite direction to the field, and hence they acquire an average velocity. So you can say drift velocity denoted by Vd is nothing but the average velocity gained by electrons in traveling from one end to another end under the influence of external field or potential is called drift velocity. This you can express in different ways. Drift velocity can be expressed in terms of current as you can remember as I is equal to NEA Vd. So Vd is equal to I by NEA. When I by A, current by area is current density. So you can also express this as J by NE. These are different ways of expressing drift velocity. Drift velocity can also express in terms of field. How to express in terms of field? E, capital E by M into tau. So as velocity is nothing but acceleration to time. Acceleration by taking that what we call electric force acting on the charges is QE in the electric field, and if we equate that with the mass into acceleration, that acceleration is drift velocity by time, and if we equate it, we will get deceleration. This is another way of expressing drift velocity in terms of electric field, in terms of current, in terms of current density. Depending on the data in that position, you can use any of these equations. This is briefly about drift velocity. Then we'll see what is Ohm's law. Ohm's law. Ohm's law says that if you have a conductor, if you connect this to a potential, a battery of some potential V, electrons will drift because of the field and it will give some current. If you change this potential, the number of charge carriers collected will increase, means current increases. So if you change potential, current increases. So Ohm's law says the current through a conductor is directly proportional to potential difference across the ends of the conductor, or you can say V is proportional to I. V is proportional to I. So from by replacing this, we can proportionality constant, proportionality symbol with a constant, we can write V is equal to R into I or IR. This we can consider as mathematical relation for Ohm's law. This is not a universal law, this is just a mathematical relation. And based on this relation, we can draw one graphical relation, graphical representation. We call it as VI graph. VI graph. Usually, for conductors, current and potential difference are directly proportional. If you increase potential, current increases for conductors. Right? So, they will follow a straight line relation. If you take V and if I increase V, I also increase linearly. So they follow a straight line relation. Based on this, we can classify the materials into different types like ohmic devices and non-ohmic devices. The devices for which VI characteristics are straight line or which obey what Ohm's law. Ohm's law is for them VI characteristics are straight line are called ohmic devices. Ohmic devices. Whereas the devices for which VA characteristic graph is not a straight line are called non-ohmic devices. Non-ohmic devices. So for example, examples for ohmic conductors or ohmic devices, any term you can use, are nothing but all metallic devices or metals you can say. all metals are ohmic conductors or ohmic devices. Whereas the examples for non-ohmic conductors or non-ohmic devices are all semi-conducting materials are called non-ohmic devices. So, for example, diode, transistor, triode, vacuum tube, etc. Right? So, usually we come across the semiconductor devices, what do you call it? Diode, PN diode or semiconductor diode, and even rectifier, and what is this? Transistor, etc. You can say simply diode and transistor are best examples of non-ohmic devices. So, how can you say, you can also remember that for diode, VA characteristics, we take V and I, which will if you increase the potential, at a particular potential current starts and it follows this relation, it gradually increases the current. So, this is the VA characteristic for diode. You can also call this as forward bias VA characteristic, because bias characteristic it ensures a drastic convergence. Right? For a transistor, VA characteristics will be different. This is for diode. This is for diode. Right? For a transistor, VA characteristics look like this. V increases, then the current will increase gradually and becomes constant. We call it the saturation current will come. So, for different values, we come across like this kind of what do you call curves. This is the what do you call input VA characteristics for a transistor. Okay, so these are VA characteristics for non-ohmic devices, for diode and for transistor. Right? Whereas you see here, by using this Ohm's law, we have come across what do you call it? Proportional constant resistance here. This R will be called as resistance. From this, we can express R is equal to V by I. V by I, and we can define resistance as the ratio between potential difference across the ends of the conductor and current in the conductor gives resistance. But we have to remember that resistance does not depend on either V or I. Why? Because if you increase potential, current also increases. And hence, if you say R is equal to V by I, V increases, I also increases. The ratio becomes constant. That is why it is called as a constant. It does not depend on potential or current in the conductor, but it depends on some other factors. What are those? That is another important point. If you see the resistance and factors on which resistance depends, usually you can say resistance depends on number one, dimensions. You can say shape and size of the conductor. We call it as dimensions of the conductor. And it depends on nature of the material. Nature of the material means by using which material the conductor is made, whether copper conductor or aluminum or gold or silver or whatever it is. And it also observed that resistance also depends on temperature, and on some impurities also depends on, right? So if you observe this, as we want to revise this quickly, how resistance depends on dimensions. I am giving direct formula. You can say dependency of dimensions on resistance or resistance of a resistor is given by R is directly proportional to the length of a conductor and inversely proportional to the area of the conductor. So we write it as R is equal to some constant rho. We call it as resistivity to L by A. This gives the expression for resistance of a conductor in terms of dimensions. Whereas resistance of a resistor in terms of temperature, if you want to understand, you have to say just in thermal properties. If you remember, change in length of a conductor or change in area or change in volume. If you say delta L, directly proportional to its original length or initial length and change in temperature. And if you replace this with a constant, we will use the symbol alpha, called as the coefficient of temperature coefficient, linear coefficient. In case of change in length, similarly change in area, change in volume also is considered a similar kind of relation. That relation we will observe here. You can write a change in resistance is proportional to the initial resistance and change in temperature. Proportional to. If you equate that, we will take the constant alpha and we can write R delta R is equal to alpha R naught into delta T. This delta R is change in resistance. Final minus initial. Final means at the temperature. Minus initial temperature, if we take it as 0 degrees Celsius, so R naught is equal to alpha R naught into delta T, or you can write RT is equal to R naught plus this, or you can write it as R naught into 1 plus alpha delta T. We give you the variation of resistance with temperature, where alpha is thermal coefficient of resistance or temperature coefficient of resistance. Delta T is change in temperature. R naught is resistance at 0 degrees Celsius. R T is resistance at T degrees Celsius. Similarly, as R depends on temperature, here the parameter constant rho also depends on this temperature. This you can write it as rho at a temperature T is equal to rho naught into 1 plus alpha into delta T also can take. Okay? Based on this, you can work out some questions already worked out. You can go through them as time up. I am winding now. These are really few points. And color code resistors also just try to go through. Okay. And based on this, already I have worked out some questions. Go through them. If you have any questions, just you can take the help of these guys and send me so that I can respond. Okay. But right now, try to revise the questions which already have practiced. Okay. Even it is just a small concept, just try to go through and revise the questions already have